Hello, welcome to Modeling with Math in Maya. My name is David Lightbown. I'm the Senior Artistic Technical Director at Artificial Mind and Movement, better known as A2M, in Montreal, Canada. So before we begin, we're just going to look at the goals of this video. One of the goals is to create a math library using MELscript, and there are two parts to that. One is that we're going to look at a couple of tips and tricks, some MEL profiling techniques to be able to find out which procedure is faster than another, which will help us to optimize our MEL scripts. And then we're going to create a couple of procedures to allow us to use formulas from geometry, linear algebra, and trigonometry. The formulas that we're going to look at are going to be very simple, so don't be intimidated if you don't know a lot of very advanced math. Everything will be explained to you in a very simple and straightforward fashion with visual aids as well. Then, with those procedures, we're going to develop tools to solve problems. Essentially, what we're going to do is combine scripts. So combine a couple of scripts together with different purposes to create a tool, and then optionally add an interface on top of that so the user doesn't have to be able to understand how the tool works underneath. All they do is select their geometry, click a button, and everything works as they want. And essentially, the purpose of creating these tools is to automate tasks in a production environment. Just a quick note before we continue that a lot of the stuff that you're going to see is essentially related to modeling, but it can be used by all other sorts of disciplines. The information that you'll see would be useful to animators, riggers, special effects artists, pretty much anybody who uses Maya. And finally, one important point is you're going to be seeing a lot of math, a lot of formulas. Try not to be intimidated by what you're about to see. Try to be inspired by it. If you see something that is going to help you in your production environment, worry more about the what and not so much about the how. If you see that the what, essentially what it does for you, is useful, then maybe watch the DVD again, figure out the how, look at some of the support material and the scripts that I've included in the package, and you should be up and running in no time. So just a few points to go through in the interest of time and simplicity for this DVD. I'm not doing any error checking, so I'm not seeing if anything is too big or too small, if anything's not selected, that sort of thing. I'm going to assume that Maya is working in centimeters. Some people may work in another unit, for example, meters. In my scripts, everything is in centimeters. That's the Maya default. You can, however, if you want to, for your own scripts, use the convert unit command, which essentially allows you to convert from, say, centimeters to meters, do a calculation, and then go back into centimeters. I've tested everything on Maya 8.5, Windows XP, and an x86 CPU, such as an Intel Core CPU or an AMD CPU. Just a couple of script commands here that you can use in case the user is using something other than these three. The about command with the operating system flag allows you to find out which OS the user is using, in case for some reason that's significant. The CPU type as well. In my case, as I said, x86 CPU. If your user is using a MIPS or a PowerPC or some sort of other CPU, you can find out what CPU type it is with this command and the CPU type flag. And then finally, there's another command here called get application version as float, which gives you a floating point number, which is the version number of the application. So in this case, it would be the floating point number 8.5. If for some reason, and it does happen between versions of Maya, that commands or flags will change, you can find out if the user is using a particular version of Maya. Again, I haven't done any of this, just in the interest of time and simplicity. And then finally, no Hungarian notation, for those who don't know what it is. Very quickly, in the case of an integer array, I would put IZ in lowercase at the beginning of the name of the variable. So instead of values, it would be IZ values. In this case, I'm not doing that. It's just going to be values. But some people feel that that's a good practice. If you want to, go ahead and do it. In these examples, I haven't done it. Just a really quick thing to go over here. What I have done to get all of my scripts to source automatically in Maya, i.e. be available in memory and ready to use, is to put them into the Maya scripts folder. Different people use different techniques. This is the one that comes with Maya out of the box, essentially. It's very simple. What you do is you put your scripts into the My Documents Maya scripts folder. And everything in there, when Maya loads up, gets sourced. And that means it gets read and put into memory. Now, if you put the name of the file with the same name as a single global procedure inside that file, it'll automatically be available to you to use instead of having to source that file first. So, for example, let's say you had a file called AutoSourceMe. And then you created a procedure, a global procedure inside that file, autosourceme.mel, with the same name minus the .mel at the end. In other words, autosourceme.mel, and then the name of my procedure is autosourceme. If you put this script into the My Documents Maya scripts folder, as soon as you launch Maya, you will be able to run the autosourceme command. It'll automatically be sourced in memory. In other words, as I said, available in memory to use. Most scripts, in some cases, you have to put the script somewhere, open it up in the script editor, select the whole thing, select execute. In this case, as long as you put it into that folder and you follow the structure, not necessary. Just one little quick command I just want to mention, the rehash command. What the rehash command does is it basically resources all the scripts in the Maya scripts folder. So for example, let's say you're working on a script and you put it into the My Documents Maya scripts folder and you modify it. You can run the rehash command to go through that folder and reread all of the scripts in there and resource them into memory. Now, before we continue, I wanted to show you just a couple of techniques that I use to debug and to profile my scripts. One quick technique that I want to talk to you about is debugging. Now, some common debugging issues with a lot of scripters are, first of all, that you have to put print commands everywhere to find out what your variables are doing and what the values of those variables are. This can be very cumbersome in that you have to put prints all over the place, you have to comment them out, uncomment them to be able to get them to print stuff again, and it's essentially a cumbersome process to have to put prints all over your code. And then finally, there's also no easy way to break out of an infinite loop. A lot of you who have worked with MelScript know that if you get into an infinite loop, a for loop or a while loop, and there's no way to get out, Maya essentially freezes in an infinite loop. There are a couple of techniques you can use to break out of that loop, and I'm going to show you one of those techniques and an easier way to use the commands. So in C++, there's something called a breakpoint that allows you to choose a line of code and say when I get to this line, then I want you to stop and I want you to tell me what the values of my variables are, or allow me to examine my code, essentially where I am. Mel does not let you do this, but what we're going to do is sort of try to simulate a system that resembles a breakpoint system that we see in most C++ development environments. So one thing that we can do is use a command in Mel called the confirm dialog command. The confirm dialog command has a series of flags. Some of the flags here that you can see that are available are B. B essentially allows you to put a button onto a little pop-up box, a dialog box that comes up and asks you to confirm a certain thing. Either do you want to continue or break. In our case, what we want to do is when we go into a loop, if we want to continue through the loop, so go through it 1, 2, 3, 4 times, we're going to click continue each time it goes through. And if we see something wrong and we want to break out of it, we just click the break button. And then what we do essentially is we're just going to wrap the confirm dialog in an if statement. So essentially here's how it breaks down. We have the confirm dialog, continue or break in backticks. And when that confirm dialog pops up to the user, they can choose to click continue or break. And if they click break, the confirm dialog command is going to return the result, a string that is the same name as the button. In this case, equals break. Okay, so we're going to do that if. The if pops up the dialog box, and if the result of that happens to be break, in other words, the user clicked on break, then we're going to run an error command, and we're going to give an error, for example, first breakpoint. Basically this, as those who use MelScript know, the error command, regardless of where you are in your code, it'll always stop the script dead in its tracks. So any point at which you are in your script, if the user clicks the break button, then it's going to stop right there. And here's an example in the bottom right of what a confirmed dialog would look like with the continue and break buttons on it. That's one way to do it. However, we're going to make it a little bit easier by actually creating a tool, a utility in this case, that's going to let you set breakpoints. And this is all part of the package that comes with the eDVD. We'll look at some of the different packages that we're going to create later, i.e. utilities, tools, and math libraries. Here's a utility. It's called dlutils_breakpoint. And what it's going to let us do is create breakpoints using the confirmed dialog, but it's been hidden inside the procedure. It just makes your life a little bit easier. So here are the inputs that it takes. In between the brackets of dlutils_breakpoint, here's what it's going to expect. First of all, the name of the breakpoint is a string. So if you have several breakpoints in your script and you want to give them different names, for example, my first breakpoint or inside the loop or something to that of that nature, then you put the name as the first variable. Then you can put a 0 or a 1, an integer, to toggle the viewport refresh. So, for example, if you were building an object in the viewport and you wanted to be able to find out what the object looks like, you can choose to be able to toggle the refresh of the viewport or not. And then finally, this is the one that's a little more complex. It's essentially a string array, basically a series of strings, so more than one string, that's going to contain the names of the variables that you want to track. So you want to see what the results of those variables are, what their current values are as you're going through your script without having to add print commands. So you put the names of those variables with the $signs as a string array. So here's a very simple example of the command being used. So dlutils_breakpoint, and then at the beginning you use after selection, so that's the name of my breakpoint, and then 1 because I want to be able to refresh the viewport. And then here's the names of the 3 variables that I want to track, x, y, and z. And here's another example of running the command again. I've called the breakpoint break1 in this case. I don't want to refresh the viewport, so I put a 0, and the name of the variable that I want to track is called x. So let's just go look at a quick example here of this, and here's an example of what the breakpoint interface looks like. So here's our script, and I have essentially 3 different variables here, as I said before, x, y, and z. 0, 0, and 10 are their contents. And I'm going to do a while loop, and inside the brackets I'm putting 1 in the condition here. So essentially, if I put true or 1, this loop will essentially never end unless I put a breakpoint inside. So because it's always true, it's going to continually go over and over and over again. However, because I put in the dlutils breakpoint here, every time it runs through the loop, it's going to pop up a box, give us the names and values of the variables that we're tracking, and then it's going to allow us the option of either breaking or continuing. And you can see here, each time we go through, we modify those variables. And then we're also going to create a sphere in here just to show you the viewport refresh. So what I'm going to do is I'm just going to minimize this and move this off to the side. I'm going to select all and I'm going to run the script. Okay, and so you see the first time we run it here, there's our sphere that was created, and we have the values of our variables. Remember, we had the 3 at 0, 0, and 10, and the first time we go through, x is incremented by 1, and y and z are also modified as well. So each time I click on continue, you see it's going to modify these values, and we can track them. And it also, again, is allowing us to view what's going on in the viewport here. So we can continue. And let's say, for example, for some reason I didn't want x to surpass the value 13. So if I click on continue, when I see that x is at 13, I know something's wrong. So all I have to do is go ahead and click on the break here, and right away it stopped, and I can see it's giving me the name of my breakpoint, so I know where in my code that breakpoint is. Of course, it also gives you the line number as well. And I can go ahead and debug it from that point on, having known a lot more than I would if I had to do the cumbersome process of putting a whole bunch of print statements, etc. So, moving on. Let's look at the 3 different libraries that we're going to create in this DVD. So as I said before, we had math libraries, utilities, and tools. So first, the math libraries. Essentially, dlmath is the prefix that I'm going to put on all those commands. DL for my initials to make it unique from other libraries that may have been done, so there's no name conflicts. And here's a couple of examples, basically anything that will allow you to do input and output in numeric values. So all of the input and output with the dlmath library is all in ints, floats, and vectors. No strings, essentially because the math libraries are only dealing in numbers. Then we have the utilities, dlutils, which are essentially support utilities to be able to allow us to do certain things that we couldn't do with dlmath. An example here is, say, dlutils_get vertex coordinates. What this will allow us to do is, if we give it the name of a coordinate, and again, as with everything in Maya, a coordinate name is usually a string. So, for example, p^1 dot vertex 0. That's a string. So, because unlike the dlmath, support utilities will allow us to use, we will be able to use strings. This will give us the vertex coordinates of that vertex. Another example here, dlutils search string array. So we go through a string array, and we're going to look for a certain word, and if it is in there, then it's going to give us either a true or false result. And then finally here are production tools. So DL tools will be all the tools that we're going to build essentially by combining scripts and procedures from DL Math and DL Utils. So we're going to build a tool for the user to use to be able to accomplish a certain task in production, and it's going to be a combination of one or more DL Math procedures and one or more DL utilities to be able to create this final tool. Now it can have non-numeric input and or output, i.e. strings, any sort of input or output we want essentially. So let's look at a really simple example. So what we're going to do is create a tool to find the center of a polygon face by combining two scripts. Remember, again, like I said, we're going to take DL Math and DL Utils and sort of put them together to create DL tools. So we're going to create a new tool called DL Tools underscore face center. Okay, and it's going to be made up of two scripts, of two procedures. One is called DL Utils underscore get vertex coords, as I mentioned to you before, and this procedure essentially finds the coordinates of the vertices that make up a face. So you give it coordinates or a face, and it's going to return to you the coordinates of all of those vertices. Okay, and then we're going to use another command in the math library called DL Math average 3D, and what this function does essentially is you give it a series of vertices coordinates, and it'll give you the average of all those positions. And with that, essentially, if we know the position of all of our vertices, and if we can average that number, then we can find the center of that face. Now let's go ahead and look at a very quick example here. I'm just going to go ahead and load a simple triangle face that we have here. What we're going to do is essentially, like I said, we're going to find this vertex, and this vertex. So all three vertices at the three corners, find their coordinates, and then the average should essentially lead us to the center. Okay? So, and we're also going to add a little interface onto this so the user doesn't have to understand how the tool works. So again, all they do is select the face and they run the tool and it works. So here we're going to load up our little tool here. Okay, so here it is. All we have to do is select our face and click create. And again, like I said, it's going to take the three using the DL Utils function. It's going to find the coordinates of the three vertices, and then using the math function, it's going to find the average of those three, and there is our average center, and it just goes ahead and creates a locator at the center there. So essentially the purpose of this exercise is just to show you how we're going to continue in this presentation. We're going to create a series of utilities in math libraries and put them together to make a tool to solve a certain problem in production. So before we continue into actually creating the tools, we're just going to look at one last utility here that I've used in the process of making some of these scripts that might help you to optimize some of your scripts as well, and I call it DL Utils Profiler. What it does is it essentially uses the timerx command, and timerx is a mel command that essentially allows you to find the start time and then run a series of commands, and then find the end time, and then compare those two times to figure out how much time has elapsed between those two. And by comparing two different times, you'll be able to figure out if one function or procedure is faster than another. So the inputs for this command are very simple. It takes three inputs. One is the name of the first procedure you want to compare as a string. The second is the name of the second procedure you want to compare as a string. And then finally, an integer, that's the number of times you want to repeat this test. So the higher this number is, essentially, the more accurate your test will be. So here's an example of a test that wouldn't necessarily be very accurate because you never know if your computer is idling or something else is happening. So here we're comparing the add function to the subtract function, and we're going to repeat that 3 times, and it's going to tell us which is faster than the other. And now here we're going to compare the function called A to a function called B and repeat that 100 times and see which one's faster. And essentially what this command does, this utility, is that it's going to return a report to tell you how much faster one is compared to the other in seconds, rather in milliseconds, and also in percentage. And we're going to use this command at certain points throughout our presentation later on to compare certain, for example, mathematical formulas or approaches to a problem. And by using this profiler, or just simply using timerx, you should be able to profile your mel scripts and be able to see what's faster than another approach. So we're just going to quickly look at a very simple example here called simple versus complex. And so here in our script, we have one procedure called simple and one procedure called complex. So here the simple is, as you would have guessed, very simple, essentially just 1 plus 1. And the complex is, as you expected, again, very complex. We're doing a logarithm, a square root, power, and then of 2 random numbers. And we're doing that 3 times. We're going to pass it to 3 different variables. And what we're doing, again, as I described before, we're using the dlutils profiler command, and we're going to compare simple to complex, and we're going to repeat this test 10,000 times to be as sure as possible that it's very accurate. And it'll just take a couple seconds to run, so I'm going to select this and run it. And the results are going to appear up here in the history panel. So we can see here that simple is 10% faster than complex. So we'll erase that and run it again. There, simple is again 10% faster. One more time. Simple 17% faster. So the number is variable, but essentially it'll give you an idea of how you can compare 2 different functions and have a very accurate reading as to how much one is faster than the other. And then once you know which one is faster, of course, you go for that one, and your user will have a much more interactive and faster experience with your tool. One last point before we continue, there is a reference sheet that you can use to follow along. You can either print it out or just look at it in electronic format while you're watching the DVD. So it contains a series of formulas that we're going to see and little bits of Mel script that you can use. So if you want to use it to write some notes on or be able to follow along or print it out and hand it out to some people who are going to be watching the video, you're welcome to do so. So let's begin with our first tool here called the mesh splitter. And what the mesh splitter does is it analyzes a mesh, and regardless of the size of the triangles that make up this mesh, it's going to break it up into equal sized pieces with an equal surface area. The purpose of this is in some 3D engines, the mesh is used to allow artificial intelligence to navigate around the mesh, and it's always best to have this navigation mesh broken up into smaller pieces, and that's essentially one of the purposes of this tool. It could be used for all sorts of other things, but essentially the main purpose is just to look at how we can break up a mesh into smaller pieces, but regardless of the size of each triangle, we want an equidistant surface area. So essentially we would create a little tool like this that would allow us to set the maximum area, so in this case it would be 50, and then it'll break that mesh up into smaller pieces. So, what do we need to be able to split a mesh up into pieces of equal size? Well, we need to know 2 different things. One, we need to find the lengths of the triangle edges. So go through each triangle and find the lengths of their edges, and then calculate the area of a triangle. So if you know the lengths of the edges of a triangle, then you can find the area of that triangle. So we're going to need 2 math formulas. One of them is going to be the distance between 2 points. That's going to be the length of our edge. Since edges are made up of points, the distance between those 2 points should essentially give us the length of that edge. And then finally, a formula for the area of a triangle. So let's start off with distance between 2 points. So I'll show you the wrong way to go about finding a mathematical formula for something. It's very easy to fall into this trap, but let's go ahead and look at it. Essentially, we can find a formula for the distance between 2 points. Now, for example, you would have point A and B. You take their x, y, and z coordinates. You subtract one from the other. You do the power of that to 2. You find the square root, and then you write a big script to be able to do all of this stuff. Well, hold on. The right way is essentially to go ahead and see if there's something that already exists. And I know it's tempting to crack open a formula and find out how everything works, but it's not always the best way. Always try to see if there's a mel command that already exists. And the reason why I put this slide in is because I did the exact same thing doing this presentation. I wanted to find the length between the length of an edge, the distance between 2 points, and I started looking into formulas and ways to do it until I stumbled upon the fact that Maya already has a command to do this. So after I did that, I realized that every time I want to come up with something new, I should always check to make sure that something does already exist. It sounds like something pretty basic, but usually this becomes a problem not because people don't know, but because it's very tempting to be able to see how everything works. And while I understand that, in a production environment, it's not always the most efficient way to do things. You should always see if somebody else has already found a solution to your problem. And again, another reason why it's always best to look for a mel command that already exists is because generally, but not always, mel commands are always faster than a couple of lines of mel script. And the reason for that is because a command is essentially something written in C++ and compiled to work just on your CPU. So it's all a bunch of binary zeros and ones, and it's going to work much, much faster than a script, which is essentially going to go through character by character of the script and then run it afterwards, what's called interpretation. This is usually a lot slower, not always, but generally a lot slower than a mel command. So the command to find the distance between 2 points is called mag. It stands for magnitude. So what we would do essentially is use this command. The input is very simple. All it is just the position of 1 point as a vector essentially being a number with XYZ coordinates. Okay, so a point in 3D space. So here's the syntax of what you would do. You would call the mag command and then pass it a variable, a vector called point. Now, the reason why it only has 1 instead of 2 points, remember we were comparing 2 points. Somebody might be asking, well, I thought we were comparing 2, not just 1. Well, the reason why is because the other point is considered to be at 0, 0, 0. And to zero out a vector, essentially what you want to do is subtract one from the other. So, for example, let's say you wanted to know what the distance is between the numbers 5 and the number 2. You want to know how much distance there is in between those two. Well, very simply, you would just subtract one from the other. So you know that 5 is 3 larger than 2, because 5 minus 2 is 3. Well, by subtracting a vector from a vector, it's essentially the same thing, but in 3D. So what we could do is run the mag command, and inside the mag command, instead of just putting point, we could put 0.1 minus 0.2, and then that'll give the difference, and then find the magnitude or the length of those between those 2 points, and therefore the length of that edge. And finally, the output of that command, of the mag command, is a floating point number, which is the actual length of that edge. So now we know how to calculate the length of an edge. Now we need to know the area of a triangle. So we take the 3 edges of the triangle, and then we want to figure out its area. So again, we're going to attempt to find an existing mel command instead of creating a mel script, just like we did before. So first, we look at something called polyevaluate, which has a flag called area. It's a good alternative. However, the problem is that it only tells you the total area of an object, not an actual component, i.e., a triangle face. So again, it's only made to work on components. Another option would be the polyselect constraint, geometric area. Now, while the polyselect constraint allows us to work with components, the problem is that you have to be able to select your components every single time. So see, it's constrained to a component selection, but it's essentially made to filter polygon selections, not really to be able to give the area of an object. So we're constantly going to be selecting a face, selecting another face, and usually in MelScript, when you have to do any sort of selection while you're running a script, it'll slow the script down significantly. So it's best to stay away from that sort of thing. So we pretty much assume that we have to make our own solution to this problem. So we're going to create a new script to calculate the area of a triangle. So the formula for the area of a triangle, as many of you may remember from pretty simple beginner geometry in high school or even in elementary, would be length times width divided by 2. Now, a better alternative to length times width divided by 2 is length times width multiplied by 0.5. Now, the reason why is that multiplication in almost all programming languages and on the majority of CPUs is always faster than division. This is true for the vast majority of CPUs. Why exactly is usually a closely guarded secret by the CPU manufacturers, such as Intel or AMD. They'll never really give up the reason of why or how essentially their multiplication or division works on their CPU, just that it's a lot faster essentially. So any situation in which you have to divide by 2 is always best to multiply by 0.5. Again, this is another tip that you can use to speed up your scripts. So here, again, another example here. This is slower. Length times width divided by 2 is slower than multiplying by 0.5 in this case. So we talked about our profiler before. Now we're going to use our DLUtils profiler again here to compare division against multiplication. So we're going to jump back into Maya here and see that we have two different procedures here. One called division and one called multiplication. So what I'm doing in the division procedure is about a million times here I'm going to be taking this number 8765432 and dividing it by 2 and just putting that into a float variable. Now in the multiplication I'm going to be doing the exact same thing. A million times I'm going to loop through going 8765432, but instead of dividing by 2 I'm going to multiply by 0.5 and pass that to a float variable. So I'm going to compare these two. The reason why I'm only doing it 3 here is because I'm already doing it a million times, so I've already got a pretty accurate reading. So what we're going to do is go ahead and run this and see what our results are. I'm going to wait a couple seconds. So we can see here right away multiplication is 17% faster than division. I'm going to clear that and run it one more time. And there again, multiplication 15% faster than division. So you can see here, you could run your own tests if you want to with the DL Utils profiler, but in the majority of cases, I would always recommend going with multiplication over division. So continuing on with the mesh splitter now, what we're going to do is we're going to, again, because we're creating our own command in our math library, so dlmath_area, this is going to be to calculate the area of a triangle. So our input is going to be the coordinates of the 3 vertices that make up a triangle as a vector. So we want to have the coordinates of those vertices so that we can figure out the lengths of those edges. So essentially here's an example. We would give it vertex 1, vertex 2, vertex 3, and pass that to the dlmath_area procedure. So the first step, once we can do that, we have our 3 vertices, and then we're going to calculate the length between the 3 edges of the triangle using the mag command. So again, mag vertex 1 minus vertex 2. Then we find the shortest 2 edges. So we can use a command in Mel called sort. What sort will do is either alphabetically or numerically, it'll order an array into the essentially in ascending order from smallest to biggest, or essentially say from A to Z in the case of an alphabetic order. And it's going to allow us to find the 2 shortest edges. If we put something in order, the 2 shortest are essentially going to be 1 and 2. And if we have 3 things, the third is going to be the longest, or essentially the largest number, the longest edge. So once we know the shortest edges, then we can take those 2 and then return the triangle area as a float by taking those 2 shortest edges, which are going to be our length and width, and multiply that by 0.5. Again, using 0.5 and multiplication because we know that it's going to be faster. Just before we continue, some people who know a little bit more about advanced mathematics may say that there is a more accurate method for calculating the area of a triangle as compared to length times width divided by 2. It's true. There is a more accurate yet slower version. It's this. Again, I wanted to try to keep things simple for this presentation. So here it is if you would like to use it. It's a little more accurate, but again, you can see there's a square root. There's a couple of more multiplications and just a little bit more calculation necessary. So it's up to you if you want to use it. The script is available to you in the package if you would like to use this formula instead. So now that we know how to find the surface area of a single triangle, now we need to go ahead and find the surface area of a series of triangles in a mesh. So to do that, we're going to create a tool, again, which is going to be a combination of several math and utilities functions. We're going to create a tool called dltools_getTriesByArea. And essentially this tool takes 2 inputs. It's very simple. One of them is the name of the mesh as a string, and the other is the maximum size of each piece as a float. So for example, let's say you had a mesh called mesh and you wanted to get a piece up to 10 units in terms of surface area. You would use the command like this. So the way it works essentially is you start from a polygon face in a corner. And the reason why we do that will be very clear. Essentially, when you do booleans or combines in Maya, sometimes the face 0 is not always going to be in the corner. Sometimes it'll be at the center. And if we grow out from the center, we're going to eventually end up cutting off certain parts of the mesh. You can see that these 2 are isolated, and that's going to cause some problems. So we're not going to do that. The way to do that is very simple. First, we're going to find the bounding box of this object. So the bounding box, you would imagine, looks something like this. When you use the xform query bounding box command in Mel, what it does is it gives you 2 numbers. One of them is the lower right-hand corner, and the other is, you can imagine, the upper left-hand corner. And what we can do is find the closest face to one of these points. In this case, we would take one of the two numbers of the bounding box and find the closest face to that point. What we can do is use a plugin in Maya 8.5 called Nearest Point on Mesh. In previous versions of Maya, it was called Closest Point, or Closest Point on Mesh. In this case, we would use the variables, the flags query and closest face index. And what that's going to do is allow us to feed that command a point in space, in this case, one of the bounding box points, and it'll return to us the closest face on a mesh. And then from that corner, then we can start growing out and measuring the size, the surface area of these triangles, and then once we've reached our max, then we break them off. What we're going to do to expand the selection, you could use a grow, and as you know in Maya, many of you may be familiar with the grow and shrink commands. However, a more trustworthy way to do it is to use polylist component conversion and convert to a vertex to a face, and then back to a vertex and back to a face. Essentially what this does is it's the same thing as a grow or a shrink, but sometimes grow and shrink stops working on certain meshes. So this is a pretty foolproof way to do a grow and a shrink without having to worry about that stuff not working. And then you keep growing your selection and keep running dlmath area on each triangle in your selection until you reach your max. So again, you keep looping until you reach your max size, and then once you've reached your max size, then you return all of the names of those faces, those triangles, as a string array. So here's essentially what the loop would be going through when you run this command. First of all, you want to find out if your entire mesh is already larger than your maximum area. This is just a bit of a security check. Imagine that you had a mesh that had a surface area of 9, and you wanted to find out, have it give you chunks that were a total surface area of 10. Well, you've already surpassed the maximum area of the whole object, so there's no point in actually entering into your command at all. So remember the polyevaluate command that we saw before with the area flag? This is the command that allowed us to find the area of an entire object. Now, we didn't want to use this command because we wanted to find out the surface area of a single triangle. But in this case, we can use it to find the surface area of an entire object and compare it to the variable that the user has put in for the maximum size of each chunk. And if that size has already exceeded the maximum size of the object, then there's no point in actually starting into this process at all. Then if that's not the case, then we're going to get an array of faces up to that maximum area size. So we would have an array, in this case we would call it selection, and I'm going to run the dltools get tries by area command and pass it over to that selection. So cell essentially is going to hold the names of all of the faces that we're going to break off. And then finally we're going to separate the faces. You could essentially, like doing an extract in Maya, now you could use Maya's default chip off function, or you could use the dltools_chip off function that I created, which is an alternative to polyseparate, which does a couple of extra cleaning up utilities to be able to ensure that geometry is as clean as possible. So let's go ahead and take a look at the tool in action. So just one thing I want to point out before we begin, one of the main reasons why we're doing this is essentially if I zoom out, you can see that some triangles are much larger than others. So one way that somebody may consider solving this problem of trying to get the surface area would be essentially just to break up the mesh by a number of triangles. Well, we can see that if I select, say, example, these triangles here, and for example, these ones over here, you can see that it's the same number of triangles, but it's definitely, clearly a different surface area. So by breaking it up by using our tool, we are going to have a much more accurate surface area size, and all of these chunks will be essentially a similar surface area. So let's open up our little mesh splitter tool here, select our mesh, and we're going to basically ask it to break it up in chunks of 50 units or smaller. So I'm going to click on split mesh, and it's going to start breaking up the mesh into pieces. And you can see that I've asked it to refresh after it creates each chunk of mesh. And now if I go ahead and look at it from the top here, you can see that each mesh is pretty much equal size. I'm just going to separate them here, and you can see that they're all pretty much more or less the same surface area, just as we requested. And if I go into wireframe, you'll see it's going to be a lot clearer that regardless of the size of these triangles, you can see here this one has very small ones, this one has very large ones. They're all essentially more or less the same surface area. Okay, so one last point before we move on to the next segment. If you happen to have some n-gons in your object, and n-gons are essentially defined as faces with more than 3 vertices, so quads or anything higher than that, there are a bunch of different approaches. One is that you can triangulate the entire object and just use a polytriangulate command to be able to do that, and then calculate the area of the object. Of course, this means that geometry will change. Another approach is to extract the face and calculate the area of the new object. So very simply, select the face, do a poly chip off, and then go ahead and use the poly evaluate command with the area flag. Again, this is another possibility, but again a bit messy because you're creating extra objects and then deleting them afterwards. Another option, of course, is to triangulate the face directly on the object and then calculate the area of the new triangles. So again, using the polytriangulate command and then using the dlmath_area command that we used. So again, if you want, everything that you've seen so far has been with triangles, but if you want to do it with objects that are necessarily non-triangulated, you can choose one of these 3 approaches. So our next section is entitled Procedural Stairs. In this section, we're going to create a tool that's going to allow us to create stairs from one floor to another. You can see here represented by the red block and the green block along this yellow line. Essentially, the tool will allow us to choose a number of steps and the width of each step. And it will procedurally figure out exactly how big each step should be, so that when we put them end to end, that they perfectly line up, they're flush with each other, and that they are perfectly lined up with the first floor and the second floor that they're going to connect. So what do we need to be able to procedurally create stairs? Well, first of all, we need to calculate the dimensions of each step, so the width, height, and depth of each step, so that they perfectly line up and they're all equidistant. And then finally, we need to plot evenly spaced coordinates along that yellow edge to be able to figure out where to place each step going up towards the second floor. So the math formulas that we're going to need to do this are essentially the Pythagoras theorem and 2-dimensional barycenter coordinates. And some of these you may already be familiar with. Let's go ahead and do a review of them. So Pythagoras, you may remember from high school. Essentially, it is a concept related to the hypotenuse triangle. Now, what is a hypotenuse triangle? A hypotenuse triangle is a triangle with 3 edges, each with 3 different distinct names: adjacent, opposite, and hypotenuse. And I have an example here in Maya. Here's our hypotenuse triangle, again with our adjacent, our opposite, and our hypotenuse up here. So one important element of the hypotenuse triangle is that it always has a 90-degree angle between adjacent and hypotenuse, rather adjacent and opposite. In this case here, we can see adjacent and opposite have a 90-degree angle here. And hypotenuse is the longest edge. So again, you can see in this example, the hypotenuse is longer than these other 2 individual edges. Now to figure out the length of the hypotenuse edge, essentially you take the length of the adjacent, you square that, add it to the square also of the opposite length, and that'll give you the hypotenuse squared. So the square root of that, of the hypotenuse, is essentially going to be the length. So here you saw this example. So again, if we take this edge and square it, this edge and square it, it'll be equal to the length of this edge squared. Okay? So here's an example of using the Pythagoras theorem to find the length of the hypotenuse. So let's say, again, we remember that the formula is adjacent squared plus opposite squared equals hypotenuse squared. So imagine, if you will, that we have the lengths of the adjacent and the opposite. So let's say the adjacent is 4 and the opposite is 2. In this case, this happens to be the case. We have the length of 4 here and the length of 3 here. And that'll equal the hypotenuse squared. So if we square those 2 numbers, 4 becomes 16, 3 becomes 9, and that equals the hypotenuse. If we add them together, that's 25, therefore the hypotenuse is 25. The square root of 25 is 5, therefore the hypotenuse is 5. So you can see here, again, the length of this edge is 5, in the case where we have 4 and 3. So let's just move this handle along here to see these numbers change. You can see as this number down here, the adjacent length changes, it's going to affect the length of the hypotenuse. Again, we can move all these edges and get a different reading on this here, but we can essentially confirm that 4 and 3 does equal the length of the hypotenuse here. So there is a command built into Maya in Mailscript called hypot, and what it allows us to do is to calculate the hypotenuse. The inputs are essentially the length of an adjacent edge and opposite edge as a float. So we have to know the length of those edges. So for example, here again, as I said before, if we have 4 and 3, it's going to return 5 for the hypotenuse. And as we saw in section 1, to find the length of an edge, we use the mag command, which stands for magnitude. So we would automatically also, this tool will automatically put your edges to the power of 2. So you saw before how you had to take the length of the adjacent and the opposite and put it to the power of 2. Well, Hypot automatically does that for you. There's no need for you to do that. However, one limitation of this command is that it's designed only to find the length of the hypotenuse, as you'd imagine from the name of the command, hypot. What if we have, for example, the length of the hypotenuse and the opposite, and we want to find the length of the adjacent? Or vice versa, we have the length of the hypotenuse and the adjacent, and we want to find the length of the opposite. Hypot does not allow us to calculate this, unfortunately. So what we would have to do is modify that Pythagoras theorem to find an edge length other than the hypotenuse. It's fairly simple. Essentially, whenever you, in mathematical formula, whenever you move variables around either side of the equal sign, if there's a plus, it should become a minus, and if you have a minus, it should become a plus. So here in this example, before, the Pythagoras theorem was adjacent plus opposite equals hypotenuse. Now, if we're going to move these words around and swap them over the equal sign, we're going to have to switch the sign. So if we, for example, in this case, switch places with the opposite and the hypotenuse, the plus has become a minus. And the same would be the case if we switched the opposite, if we switched the hypotenuse with another one. We can also use the abs command. Abs is a command in Maya that allows you to turn a negative number into positive. Any negative number, it'll just essentially cut the negative sign off the beginning. So we always want to make sure we have a positive number in this case. Now we can ensure by which order we put the hypotenuse and the adjacent in when we subtract one from the other that we're not going to have a negative number. But just to be doubly sure, we can run the absolute command on the result to make sure that if it's a negative number, it's always going to be a positive number, because we can't essentially have a negative length of an edge. We always have to have a positive length of an edge. So here's essentially what we would do. We would put one edge to the power of 2, another edge to the power of 2, because, again, remember, Hypot does that for us. But in our case, we're actually going to be rolling our own hypotenuse Pythagoras command. So first we do the 2 to the edges to the power of 2, and then we do the square root of one edge minus the other to find the length of the hypotenuse, or whatever other edge happens to be the one that we're looking for. So now, one quick note here about calculating exponents. You saw before that I was using the POW command, and what the POW command lets us do is put things to the power of a certain number. In this case, we'd be putting this edge to the power of 2. The problem is that for smaller exponents, i.e. power of 2, power of 3, the POW command is actually slower than multiplying this by hand. So you can see here in the first case, we've done POW edge to the power of 2. In the second case, we've actually just done edge equals edge times edge, which is actually the same thing as doing something to the power of 2. If we wanted to the power of 3, we could do edge times edge times edge. Now this is the preferred method for those who want to condense their code a little bit. You can just do edge times equals edge. It's going to multiply edge by itself and then return the value to itself. So this is essentially a lot faster than actually using the POW command. So this is a rare case where using the actual MEL script is faster than a MEL command. And you'll see, and I mentioned that before, that if you ever have a choice between a command and a script, you should always go for the command. But I'll show you the limitations of this and essentially when it's good to use one and when it's good to use the other. So I have an example here called power multiplication. And I'll go ahead and open the script editor here. So if I go and take a look at this example here, you can see that I have two functions, one called power and one called multiplication. In power, I'm, again, 200,000 times in this case, I'm going to take x, and what I'm going to put into x is 5 to the power of 16. Okay. In the second procedure, called multiplication, instead of using power, I'm actually multiplying x 16 times in this case. 1, 2, 3, 4, 5, all the way up to 16. Okay. And then finally, I'm going to use, as before, my dlutils underscore profiler function to be able to compare power versus multiplication. So let's bring both windows back here, and we'll clear the history. And I'm going to run this command. And you can see that in this case, power is 12% faster because I'm doing something to the power of 16. So I'm going to run it one more time, and we'll just see the results. power there is 27% faster. Now watch what happens when I lower this to the power of 2. So instead of going to the power of 16, now we're going to the power of 2. And I'm going to remove all of this extra stuff here. Now I'm just going to be multiplying 5 times 5. So let's clear the history window and run this again. And now you can see that multiplication, in this case, is 90% faster. One more time. And we can see again, multiplication 144% faster. So you can see for smaller exponents, it's much faster to use just a simple multiplication sign in this case, instead of using the POW command. When you're using anything higher than 2 or 3 or 4 exponents, then it's usually best to go with the POW command. But otherwise, always best to just do, in this case, for example, 5 times 5, or 5 times 5 times 5 in the case of when you're cubing something or using an exponent of 3. So let's move on. Now, what we're going to do, again, is, as I said, we're going to create our own alternative to the to Maya's hypot command. We're going to call it dlmath_pythag. And the reason why we've made this command, and we don't want to have the user have to remember either the hypot command or the pythag command, which one do I use. We're just going to make one function that sort of encapsulates all of those together. So the inputs are, the first input is an integer that's either sort of a toggle, it's on or off, to decide whether you want to use Maya's hypot command or whether you want to use the technique that we developed to allow you to find the length of the opposite or the adjacent instead of just the hypotenuse. And then the second, the other inputs that it takes, of course, are the lengths of the two edges as float. So it takes 3 inputs, one to toggle if we want to find the hypotenuse or something other than the hypotenuse, and the other input's essentially the length of the 2 edges that we want to calculate. So, for example, in the case that we put a toggle to 0, we would just use Maya's hypot command. So in this case, we run the command, we say, here's my toggle, it's going to be 0, so I want to find the hypotenuse. So just use the hypot command, here's the adjacent and here's the opposite. And if we put the toggle to 1, then we're going to use the command that we created ourselves, the square root edge minus edge. So in this case, dlmath_pythag, and we're going to put the flag of 1, and then we're going to pass it the hypotenuse and the adjacent. Or we could just equally pass it the hypotenuse and the opposite. So now that we know how to calculate the length of any edge in a hypotenuse triangle, let's move on to the next formula, which is two-dimensional barycentric coordinates. And they're actually very, very simple. So essentially, what a barycentric coordinate is the average of 2 points on an edge. So what you want to do, for example, is to find a point along an edge, and what you do is you average the coordinates of the 2 points that make up that edge to find a point along the edge. So essentially what you would do is calculate the coordinates between a start point and an end point. So what you would do to find the center of a point, so whenever we want to find the average of something, we usually add them together and divide by 2. Of course, in our case, the most optimal way to do that would be to multiply by 0.5. However, what if we wanted to find something that's not at the center, or not essentially at the center point of that edge, not equally between those 2 points? We want to find something that could be at any percentage along that edge, either closer to the start point, closer to the end point, or somewhere in between. So the formula for this, it looks intimidating, but don't worry, I'll break it down for you. It's going to be very simple. The start point multiplied by a percentage of where we want to find a point along an edge, plus the end point, the coordinates of the end point, multiplied by 1 minus the percent. And in this case, the 1 represents 100%. So let's go ahead and take a look at how that works. Essentially, the percent, as I mentioned before, the 1, is a float between 0 and 1. So 0 equals 0%, 1 is 100%, 0.5 is 50%, 0.25 is 25%, and so on. So if you wanted to find a point 10% from the start, okay, so 10% of the start and 90% of the end, so again, closer to the end, the coordinates of the end point, you would do 1 minus 0.1, which would essentially equal 90% from the end. So 1 minus 0.1 would be 0.9. So here's how the formula would break down. We would take start multiplied by 0.1 plus end multiplied by 0.9. Very simple. Again, 75% from the start, we take 1 and subtract 0.75. That becomes 0.25, or 25% from the end. So this would be essentially 75% towards the start and 25% towards the end. So more towards the start point. So we take the coordinates of start, multiply by 0.75, and then take the coordinates at the end and multiply by 0.25. So I'll show you a visual example here that'll make this a lot clearer to understand. If I go ahead and open this example here, which is right here. So here is our edge. So here's our start point and here's our end point. Okay, and here's the formula up here. Remember, start multiplied by percentage plus n multiplied by 1 minus percentage. So right now we're at 50-50, and the point, our resulting point, is right in the middle. Now if I move this down towards 25%, notice how the other side is going to react accordingly. As I said here, if this was 25, we would take 1 and minus 0.25. Here we're about 25% here, which would result in 75%. So by taking the coordinates of this point and multiplying by 0.25, and taking the coordinates of this point and multiplying by 0.75 and adding them together, we result in this point here, this purple point, which represents this formula in action. So you see, as I slide this along, you get a very easy, a very obvious visual idea of how this is supposed to work. If I slide it all the way to 100% on the red, it's going to go all the way to the start point, all the way to the bottom, it's going to go all the way to the end point, and anywhere else in between. So what we'll do is create our own command called dlmath_berry2d. The inputs are essentially going to be the percentage as a float and the coordinates of the 2 points as vectors. So here, again, remember we're going to use our formula, start times percentage plus end times 1 minus percentage. So here's an example of how we would use berry2d. So 0.1, so 10%, and then the start point and the end point. And the output coordinate is a vector. It's going to output the coordinate of our new point, of our point along the edge as a vector. So now what we're going to do is combine those two previous tools, the Pythagoras tool and the barycentric coordinates tool, to create our stair maker. So the inputs of our stair maker tool, one of them is the number of stairs as an integer, so we want to know how many stairs we're going to build, and the width of the stairs as a float. This is essentially a non-essential variable, but it allows us to be able to control the creation of the steps. Finally, we need to know the name of a NURBS curve as a string. This is the curve that we're going to build the steps along. Okay, so if we run this command, here's an example of how we would do it. If we wanted to build 10 steps with a width of 5 along an object called curve, then we would run it dltools_stairmaker. We want to build 10 stairs with a width of 5 along a curve called curve. So here's essentially how dltools_stairmaker works under the hood. So first we have to find the coordinates for the start and end points of the curve. So let's go ahead and look at an example here. You saw this example in the beginning. So here is our first floor and our second floor. So we need to find the coordinates for the start point and the end point of the curve. So what we're going to do is look at this curve and basically find the start point and the end point. So those 2 points here. So what we will use is the xform command, and we're going to query the world space, a translation of those 2 points, to be able to find their coordinates in world space. Then we want to find the length of that curve, the length of this curve here, the yellow curve. Again, we're just going to use the trusty old mag, and we're going to subtract the start from the end, and that's going to give us essentially a floating point number that's going to represent the length of the curve. Then we need to find the hypotenuse for each step, and this is where it gets a little more interesting. What we're going to do is take the length of the curve that we just found using mag, and we're going to divide that by the number of steps. So let's take a look here. Let's say we have the length of our curve here, and we're going to divide that by 5. Okay, so what we've done is we've separated this into 5 pieces, and that divided by 5 is going to give us this length here. Okay, and if we put up this this triangle marker here along here, and you can see that that is essentially going to represent our hypotenuse. Okay. So now that we know the hypotenuse, we can essentially also figure out, by figuring out the distance between these 2 points, we can figure out the adjacent. And now all that's left to know is the height of each step. In other words, figuring out the opposite. So by using our command, dlmath_pythag, we're going to put, first of all, the flag of 1 at the beginning to say, I know the hypotenuse, I know the adjacent, I just don't know the opposite. So if we put these 2 numbers in, it's going to allow us to figure out what the height of each step should be. So here we go. We've figured out essentially the depth and the height of each step, and the user also inputted the width. So there's no need for us to figure out the width. So that's how we're able to figure out the dimensions of each step. And then finally, we build the step. So we're going to essentially, in this example, use a polycube command with the width, height, and depth that we generated by figuring out all of their dimensions before. And then finally, using the barycentric coordinates, we're going to evenly place steps along that curve. So again, we're going to use dlmath_bary2d, and we're going to take the percent of the progression along the step, and then the start point and the end point to figure out points along that step that we want to, along that curve that we want to place the steps. So in this example, let's say here that we've decided to cut this into 5 sections. We want to use the barycentric coordinates to find out what the coordinate is at 20%, 40%, 60%, 80%, and 100%. So we can place each of those steps that we built, figuring out the dimensions using Pythagoras, and figuring out where to place them by using barycentric coordinates. So let's go ahead and use that tool. So we're going to launch it here, and I'm going to select the step, and in this case, the curve, and in this case, I'm going to build 5 steps. So there's our 5 steps. And if I want, I can go ahead and move this object, say, further down like this. And let's say we want to build 20 steps instead. So we'll go ahead and do that, build the steps. And you can see there's our 20 equidistant steps that are essentially razor sharp towards each other. I'm going to go ahead and undo that. And then let's do sort of a long staircase. And let's make it something like 100. And we're going to change the width to, say, 30. Select our curve and build the steps. And there we go. We've got a long series of steps in between those 2 floors that again are perfectly sharp against each other, perfectly aligned to the first floor and the second floor, and essentially was pretty painless to build. All the user had to do was select their curve and click on a button. Our second to last tool is entitled Ambient Occlusion. What we're going to do is take this mesh and go through it edge by edge and find the faces that are connected to each of those edges, find their normals, and compare them. And that's going to allow us to figure out what the angle is between those faces. And then with that, we're going to have this tool that's going to let us set the maximum angle and the intensity of the shadow to be able to create a false ambient occlusion, in this case using vertex color, on the mesh. So to do that, what do we need? First of all, we need to be able to find the angle of adjacent polygon faces. And then we need to determine if they're facing each other. And if they're facing each other and they're close enough, we're going to put a lot of shadow. And if they're spread apart, we're going to put very little shadow. So the math formula is required to do this. First of all, we need to understand normalized vectors. We need to understand angles. And there are 3 different sections that we're going to look at in angles: dot products, radians, and degrees, which are all related, and you'll see how. And then finally, we're going to look at vector intersection. So let's just take a quick look here. First of all, the anatomy of a polygon face normal. So it is also sometimes known as a unit vector or a normalized vector. A unit means essentially has a length of 1. And normalized also means that it's been transformed to have a length of 1. As I said, it represents an arrow with a length of 1. And the base of the arrow is always considered to be 0, 0, 0. And that's one thing that some people don't quite understand about normals sometimes. When they start looking at them, they expect them to have 2 numbers, start and end. Well, essentially, the start is always considered to be at 0, 0, 0. It's the end that essentially is represented in the numbers, in the coordinates of a normal. So in this case, the tip of the arrow is always going to be defined by a vector. So for example, let's say we had a normal like this. So if it was 0, 1, 0, which means it points up in the y direction. So let's go ahead and look at an example here. Here we have our x, y, z coordinates. And so if we had our point essentially was 0, 1, 0, as you saw here, our normal is going to be 0, 1, 0. It's essentially 0 in the x, 0 in the z, and 1 in the y. So that essentially represents an arrow pointing straight up like this. And so therefore that would be the normal for a plane flat to the grid like this. You can see that I can only see one side of it. It's because the normal is pointing upwards in that case. Or we could have, say, for example, one that's between y negative and z negative. Now, the reason why it's 0.707 for both the y and the z is because, as I said before, a normal by definition always has to have a length of 1. So if you were to measure that length of this arrow, essentially that goes to 0.707 and 0.707, it would essentially have a length of 1. And I'll show you that near the end here. So again, we have a point in the negative z and in the negative y. It's right there. So then again, that would represent an arrow pointing in this direction, and the face that would have that sort of normal would look a little bit like this. Again, like I said, facing in that direction. And now just one more example. We have it diagonally towards x, y, and z positive. So in this case, the coordinates would be 0.577 for all three. Again, all of that, if you measured the distance, would all line up to 1. So again, let's take a look at that. We had positive in the x, y, and the z. Again, it would represent an arrow that looks a little bit like this. And the polygon face that would be associated with a normal like that would line up essentially like that. You can see how they're perpendicular if I look from the side there. And remember, before I talked about how they all have a length of 1. If I create a sphere here with a radius of 1, so from here to here, it's a length of 1, you can see that all of those yellow locators all are sitting on the surface of the sphere, because all of those arrows that I showed you before all have an exact length of 1. So it's a very important point that a unit vector or a normalized vector has a length of 1. So to calculate the length of a vector, there is the mag command, of course, because essentially a vector is essentially an edge. And so because the base of a vector, as I mentioned before, of a normal rather, is always at 0, 0, 0, it's very simple. All we have to do is put in the coordinates of that normal and it'll give us the length. So we can use the mag command to do that. And if you need to, for some reason, set the length of a vector to 1, essentially what's called normalizing a vector, you can use the unit command that comes with mel. And what it'll do is if you have something that does not, for example, sit on the surface of the sphere, if you have an arrow that's going to go, for example, outside of its max, if it was a little bit longer, say, for example, like this, then it would allow you to normalize it, essentially put it back to a length of 1. So to find the normal of a polygon face, essentially before, as I said, we want to take this mesh and we want to go through it polygon face by polygon face and see if two faces are facing each other. And if they're very close together, we're going to put a lot of shadow. And if they're very far apart, we'll put very little shadow. And that, going through the whole mesh that way, will essentially allow us to create a fake ambient occlusion look. So to find the normal of a polygon face, we can use the polyinfo command with the face normals flag and then give the name of the face that we want. The great advantage of this is that it's faster than averaging the vertex face normals. What you could do is take, say for example, your face had four vertices. You could find the normals of all of those 4 vertices and then average them. So this technique is a lot faster than that because you don't have to sample 4 times, for example, 1 for each vertex, and then average all 3. However, the problem with this command is that it outputs the data to type string. It outputs essentially the word face normal 0 colon -1 0 0, which isn't exactly what we want. What we want is to be able to have just 3 numbers, ideally 3 floats or something in a vector. So what we're going to do is build a tool that's going to allow us to extract the face normal from a face, and it's going to return to us a vector. So the input is essentially just going to be the name of the polygon face as a string. So in this case, we would go dltools _ face normal, and then mesh.f for face, and then face 0 in this case. What it does is it uses the tokenize command to break up the string. So for example, here's what you get from the polyinfo command that we saw before. Essentially, this is a string. So what the tokenize command does is that it breaks up a string based upon a character. So what we're going to do is break it up by the colon. So what it's going to do is essentially break up face normal 0 colon -1 0 0, and it's going to split it left and right on either side of that colon. So the colon will go away, and on the left side we'll have face normal 0, and on the right side we'll have -1 0 0. So we're just going to keep what's on the right side. We're going to keep the second value, and that's going to be -1 0 0. And then we're going to break that up by a blank space. So essentially you have -1 space 0 space 0. So we're going to break it up by spaces so that we have -1, and then separately we have 0, and then separately again we have 0. And we're going to pass those 3 values into a vector. So by using these 2 tokenizes, we've succeeded in breaking this string up into pieces and then just converting the numbers. That's all we want, really. We don't want the word face normal. We don't need any of that information. All we need is really just the coordinates, i.e. -1 0 0. And essentially this tool will output that normal as a vector. So you give it the face and it gives you the normal as a vector. So there are 3 different units of measurement for the angle between 2 vectors, and we're going to look at, as I mentioned before, we're going to look at all 3. They're all related. As I said, dot product, radians, and degrees. So let's go ahead and take a look at a little chart that's going to help us to understand how this works. As I'm explaining the dot product, I'll be able to show you this. It's going to make it a lot easier to understand. So let's load up this scene here, which is going to allow us to study how angles work. So what is a dot product? A dot product is the most optimized method to find the angle between two vectors. And I'll show you what that means. Here's the formula for a dot product. Again, it's like some of the other ones that we've seen. It looks intimidating, but the results are really what we're interested in. How it works is inconsequential. It's really all in the context. So what it does is you have 2 points, A and B, or rather two vectors, A and B, and you're going to take their x's and multiply them, their y's and multiply them, their z's and multiply them, and add all that together. So it's fast in the context of computer graphics, and this is used a lot in real-time simulation because it only uses 3 multiplications and 2 additions. And in the grand scheme of things, in terms of real-time graphics, that's a very, very few calculations. So when it's used on normalized vectors, it always results in a number between 1 and -1. So if you give it 2 vectors and you pass them through this formula, the result is going to be between those 2 numbers. And those 2 numbers are going to determine an angle. So here, for example, we could use dot product to calculate the angle between 2 vectors. So 180 degrees. So let's say we had an angle, 2 vectors, one that pointed straight up and one that pointed straight down. So let's go ahead and look at that in the chart here. We're going to move this to 180 degrees, and we have something like this. So let's say we have one pointing straight up in the y and one pointing straight down in the -1 in the y. Okay? So we would do 0 times 0, 1 times -1, and 0 times 0. And that would result in 0 plus -1 plus 0, which means essentially that 180 degrees, okay, if you have 2 vectors that are 180 degrees perpendicular to, or rather parallel to each other here, okay, the result of a dot product of those 2 vectors is -1. So let's put this dot product chart up here, and you can see that the green arrow is what we're following in this case. It's pointing to the -1. Let's look at another example here, 90 degrees. So we have 1, let's say, on the x, and again 1 on the y. So let's move this back over here. Okay, so we have a 90-degree angle. I said one pointing to the side and one pointing up. So that's what we have essentially. And so again, we'll do the formula and break it down, and then the final result is 0. So 90 degrees in dot product is 0. And again, you can see here, there's our result there. So there is a command in Maya that allows you to find the dot product of 2 angles. It's called dot. The input's very simple. All you do is enter those 2 vectors. So here's an example of how you'd use it: dot vector, comma vector. And again, it would output the result as a float. As always, it would be between 1 and -1. So here, the examples that we saw before, remember this is our 180-degree example. We had 1 pointing up, the 1 in the y, and then 1 pointing down, the -1 in the y. The result is going to be -1. Again, our example of 90 degrees, 1 off to the side and 1 going up, our result is going to be 0. So how does this relate to everything else? Essentially, now you understand, here's the dot product formula up here, now you understand how all of this works. Dot product and radians and degrees are all related. And I'll just explain radians a bit to you, and you'll start to see the relation. 1/4 rotation in radians, and I'll just bring this up here. When you're talking a quarter rotation or 90 degrees, okay, in radians is 1.57, and that number will look more familiar if you see it at the half rotation, which is 3.14, or pi. Many of you are familiar with pi, which is used to calculate all sorts of things in geometry and in all sorts of other fields of math. So a radian is essentially 3.14 for 180 degrees, 1.57 for half of 180 degrees, or 90 degrees. So in this case, you can see here, a radian here is half of pi. Here it's pi. Okay, so it's always 3.14 for 180 degrees. And a full rotation would be 2 times pi, say. So if anybody's ever talked to you about radians, or you've ever had a little bit of difficulty, or you've used some commands in Maya that use radians, it's very simple. A half rotation, 180 degrees, is essentially pi, or 3.14. Okay? these are ideal for use in trigonometry because trigonometry is all based on triangles, and if you start to study trigonometry, you'll see that triangles are also related to circles in a certain way, and we'll see that probably a little bit later in a section coming up, and that, as you know, to find the area of a circle, you have to use pi. So they're related, and it's important to understand how radians work. To convert radians to degrees, there's a formula here. It's very simple. The number of radians times 180 divided by pi. However, there is already a command in Maya called rad to deg, and notice the underscores. So rad to deg, you put in the number of radians, and it'll convert it to degrees for you. So now, let's look at degrees. So I'm going to switch this over, and we are all familiar with these ones, of course. 90, 180, it's what we've been talking about so far. So a quarter rotation, of course, is 90. A half rotation is 180, and a full rotation is 360. And this is something that we work with primarily in Maya. We almost always work in degrees. It's something that we're all very familiar with. Nobody ever works, in common everyday parlance, nobody ever talks in radians or dot product. It's almost always in degrees. The thing about degrees, though, is that it has no basis in mathematics or science. It's a number that somebody came up with. Essentially, there are 365 days in the year, and when the Persians built their calendar, there were 360 days in their calendar, and they decided, well, let's make the number of rotations, a full rotation in a circle, let's make that number 360, because that's how many days there are in a year. Therefore, like many other things that have no basis in mathematics, it doesn't really correlate to any other sections. You can, as you saw before, switch between radians and degrees, but it doesn't really have any basis. You can't really take it into any mathematics and use it until you convert it to radians or dot. So if you want to convert your degrees to radians, very simple again, degrees divided by 180 times pi. And again, there's of course a handy command in Maya that allows you to do that, degrees to rad. So there is a command in Maya that does allow you to measure the angle in between two vectors, just like dot. The inputs are, again, two normalized vectors as vector, just like the dot. And here's an example of it being used. The important thing is that it outputs, the angle command outputs the result in radians. So for any of you out there who have used angle before and got a strange number that was something like 1.57 to 3.14, well, that's because, again, it's using radians. 1.57 is 90 degrees, and 3.14 is 180 degrees. So here's an example, again, as we saw before, one pointing up, one pointing down. Our 180 degrees is essentially going to return 3.14, and we could use rad to deg if you really absolutely wanted to have it in degrees. And again, our 90 degree angle here, one up and one to the side, 90 degrees or 1.57 if we ran the angle command on them. There is one limitation about this, though, of course, is that it only calculates an angle up to 180 degrees. And I'll show you why this is a problem in a second. Also, it's slower than dot because it has to convert back and forth. Essentially, under the hood, a lot of 3D real-time applications use dot products heavily because it's a very, very quick calculation. So in the long run, it's potentially a little bit slower than dot. So it's always better to use dot if you can wrap your brain around the concept of, as I said, 1, -1, and 0. So now let's talk a little bit about vector intersection. Now that we understand how angles are measured and some tools that we can use to measure angles, we have to compare polygon face normals to be able to see how close together they are. The problem is that comparing polygon face normals alone, can't determine if they're facing each other. And I'll show you why. What you have to do is create a context between the polygon face normal and the polygon face center. And here's an example that you'll see in a second. I'm just going to flip over to it here, and it'll be very clear to you in 1 second exactly what it is that I mean. So let's imagine that these are two polygon faces here that we have, and what we want to do is, as I said, if we have faces that are sort of very close together like this, we have sort of a crevice. We want to put a lot of shadow in here because in ambient occlusion, when there's a crevice like this, a crack or a valley of some sort, there's usually a lot of shadow inside. And if you have something like this, like a mountain, you're not going to have a lot of shadow here. You're usually going to have a lot of light. And then something in between, you'd have, say, for example, a medium amount of shadow for a 90-degree angle like this, So let's bring up these two normals here, and we'll see how this looks. So let's say that we were going to go through all of our polygon faces one by one, and we're going to look at this edge and say, okay, I have this edge. Tell me the two faces that are connected to this edge. Okay, I have the two faces. Now use, for example, the tool that we created, DL tools underscore face normal. Tell me the normals of those two faces. Okay, I've got the normals of those two faces. Now let's compare them and see what we get in terms of the dot product. What we would get in this case, of course, would be 0. As I mentioned before, 90-degree angle is going to give us a dot product of 0. Now, let's say that we moved our face like this. If we measured our two angles, what would we get? Well, unfortunately, again, we would get a dot product of 0. Because if we look at it without the normal on, this, one pointing up and one pointing to the side, and this, the 90-degree one that we saw before, is still one pointing up and one pointing to the side. There's no way for Maya to know, there's no context for it to know which one is which, and which one is pointing up, which one is pointing down. All that it knows is that this is a dot product of 0, or it's essentially 90 degrees. Now remember this this symbol that we saw before when we were measuring the angles? Remember that when I got to 180 degrees here, as I get all the way over here, it's going to flip right over. So this here is 90 degrees. But as far as the computer knows, when I run dot or angle or anything, it's going to consider these two as also being 90 degrees. So it sees no difference at all, whether the polygon is like this, the polygons are lined up like this, or whether they're lined up like this, it's still going to see it as 90 degrees. So what we have to do is create a context between these two faces to be able to understand if they're in like this, or if they're out like this. And it's a very, very simple way to do that. Essentially what we have to do is create a new vector from the center of this face to the center of this face, and that's going to be represented by this red arrow here. Okay? So if I hide this other arrow, essentially, if I look at it like this from the side, you can see that if I did a dot product on this, I would get essentially something between 1 and 0. Essentially it would be 0.5, because this is 45 degrees. Okay, remember that 90 degrees is 0, and 0 degrees is 1. So therefore it should be 0.5. And if I did something like this, okay, we're still not going to 180. These are still within 180 degrees from each other. So this would be between 0 and -1. So between 0 and -1 we have -0.5. So we know that if we measure these two normals and we get 90 degrees, and then we measure these two normals and we get either 0.5 or -0.5. We know if it's -0.5 that it should be 270 degrees, i.e. it's folded out. And if we do this and we get 0.5, we know that this is 90 degrees. So we know whether to put shadow or whether to not put any shadow. So what we're going to do is look at a tool here called DL tools underscore face normal angle. So the input is essentially two polygon faces as a string, and essentially it's going to allow us to compare two face normals and really get the true angle. And then finally, we're going to also, just for flexibility, we're going to add an integer to decide if the output is going to be in degrees or radians. It's a toggle. So for some reason, if we wanted to be able to choose one or the other. So for example, let's say we put that toggle to 0, and that would essentially mean output the results in radians. We would put in 0 and then face 1 and face 2, remember strings that are representing those two faces, and it would report to us the true angle. And let's say we put the toggle to 1, so tell me the results in degrees. Again, we put the toggle to 1 and we call DL tools underscore face normal angle, and then we put in face 1 and face 2. So let's see how this tool works under the hood, taking into account everything that we've learned up to now. So first we store the normal of the faces, and to do that, of course, we're going to use the tool that we created originally, the one with the tokenize, called DL tools underscore face normal. Then if the normals are equal, we're just going to return 180, because if the two normals are exactly the same, there's no question that they're both pointing in the same direction, and therefore that it should be 180 degrees. If not, then we have to find the angle between the vectors. So we're going to use angle, and then we're going to create that new vector, that red vector that I showed you before. This one here, okay? So we're going to create that new vector from the center of each face. And we're going to use DL tools face center. Remember, this is one of the first tools that we created originally to be able to find the center of a face. So we put the locator in the middle of that yellow triangle. So we find the face center, and then we're going to use those coordinates. to be able to create a new vector. So our new vector is equal to the center of the second face minus the center of the first face. So now we're going to compare the first vector and the new vector with dot. Remember, I told you we're going to take these two vectors and compare them with a dot product. And remember, based upon what result we get between, say, if it's going to be 5 and 0.5, it's going to give us an idea of whether it's out or in. So if the dot product is larger than 0, we're going to return 180 minus the angle. And if the dot product is smaller than 0, then we're going to return 180 plus the angle. This is going to allow us to have a result between 0 and 360 degrees, the full range, not just between 0 and 180. So now we're going to create a final tool here called DL Tools Occlusion. And what that's going to do is allow us to create the occlusion on the mesh. So the inputs are essentially going to be, first, the name of the mesh as a string, the maximum angle in degrees as a float. So the maximum angle at which we want to start creating ambient occlusion on the mesh. And then the shadow intensity multiplier. So it's going to allow us to make the shadow more intense or less intense. So here's an example of where we would make an 80% opaque occlusion, so 80% shadow intensity within 90 degrees. So we'd use DL Tools _ occlusion. The name of our mesh is going to be mesh. We want to create ambient occlusion within 90 degrees or less, and we want to have 0.8% shadow intensity. 0.8, which represents 80% essentially. Here again, 20% within 180, we would do mesh 180 and 0.2. So let's look at how this works under the hood. So first we're going to go through a list of all the edges in the mesh. So essentially the reason why we're going through edges, as I mentioned before, is that an edge is almost always connected to two faces, and we'll protect ourselves in case it isn't. But just if it's connected to two faces, then we're going to do something to it. So first we're going to get all of the edges on our mesh, and we can use LS with the flatten and long flags to get us the full listing of all of the edges on the mesh using mesh plus E. And here's a little trick you can do. You can put an asterisk, a wildcard, inside a bracket to be able to get all of the edges. In this case, an edge or any sort of component. You could use F for face or VTX and put an asterisk. It has to be in quotation marks, has to be in a string to be able to get return all of the components. So we're going to find all adjacent faces connected to each edge. Okay, so we're going to use the polylist component conversion to face. So that command will essentially, you give it any sort of component, in this case an edge, and it'll give you the faces that are connected to that edge. So now, as I said before, only if two faces are connected to the edge. If there are any more, so if there's one face, it's going to be on the side of the mesh. If there's three, it's a non-manifold edge, so it's not correct. So we're not going to process it. So only if two faces are connected. So if the size of the adjacent faces is equal to 2. Then we're going to find the full angle between the faces in degrees. So remember, we created our tool in the previous section. We created DL Tools _ face normal angle. So there, if we put 0 and then F1 and F2, then we're going to give it two faces, and we want it to return the angle for us. Now, if the angle is within the maximum angle, so remember, in this tool we also set 90 degrees at one point, we set 180, we set a maximum angle. So if it's within the maximum angle, then we're going to apply a certain amount of vertex color shadow. Okay. Now you could do this with pixels if you're so inclined. You can go in and find, if you find the UVs for those vertices that make up that edge, and then you can plot those vertices rather, the UV coordinates onto the image. Then you could create pixels there if you're more advanced in terms of shaders. But in this case, we're just going to create this with vertex color. So the amount of shadow applied to the edge is based on the angle. So the amount of shadow is going to be based on our maximum shadow. So remember, we also in the tool set a max amount of shadow. So how the max, the multiplier essentially of the shadow, divided by the face angle. So the more the faces are towards each other, the less space there is in between the faces, the more of a crack we have. If it's smaller, we're going to put a lot of shadow because there's very little light that gets into a small crack. And if it's wider, then we're going to put less shadow, less and less and less, the wider that angle is. So let's go and take a look at how this tool works. So here we have our mesh, the one that we saw before. And we're going to go ahead and open up our occlusion tool. So again, as I mentioned, we have the maximum angle and the shadow intensity. So all that I have to do is go ahead and select the mesh, and click on Create Occlusion. Now what I've done by default is I've had the tool automatically do a refresh as soon as it starts, as soon as it draws on one of the vertices, as soon as it creates a vertex color. So you can see it has the effect of painting. It's a little bit slower than it normally would be, but just to give you a sort of a real-time visualization of it working. Now we can see that the shadow, it's a little bit too intense in this case, so what we're going to do is lower that a little bit. So let's go ahead and start back from scratch here. Instead of 0.5, we're going to do is put 0.25. So we'll create our occlusion again. There you can see now it's nicer. It's a little bit lighter. It has a little bit more of that ambient occlusion look. And you can see that within a couple of seconds that we can create sort of a pass of ambient occlusion. Now you could, as I said, this is vertex coloring, so you could set this to multiply and add whatever you wanted. If you already had vertex coloring on your environment, you can go ahead and add this to it. So let's undo one more time, and I'm just going to show you here. I'm going to select a couple of faces in various spots in the environment, and I'm just going to extrude them out to get a look at how it would look with a little bit of variety in the environment. So here we'll just extrude this twice here, and we'll get a little bit of stuff on our terrain here. So now it's a bit hard to see, but we've added sort of some pseudo buildings in this case. So let's go ahead and we're going to go into object mode, select our mesh, and run our tool. And now you can see there it's painting the ambient color onto the mesh, and it's going to go ahead and finish up the rest of those pieces there. So you can see here now, because we have these faces are very close together, we get a lot of shadow in there, and it really does create a very nice sort of basic ambient occlusion look. Again, a very dark shadow in there, and the rest are all very light. So again, within a couple of seconds, you can just choose your mesh, and whichever technique you want to use, create some nice looking ambient occlusion in your environment. So let's finish off with our last section, which is sort of a bit of a bonus. It's called Water Waves. And what we're going to do is we're going to create a tool that allows us to control the waves of water. It's sort of a faked water, but it's more to understand frequency and amplitude, essentially, how waves work. So using this tool, we're going to be able to control the intensity and the speed at which this water moves. So to simulate waves of water, we need to calculate something called a waveform over time. And what we're going to do is displace the geometry, essentially that plane of water that you saw, using the waveform. And the math formulas that we're going to need to know are going to be sine and cosine. And I'll explain to you what both of those are. So sine and cosine. Essentially, sine and cosine are calculated by rotating a hypotenuse triangle around a unit circle. So remember what a hypotenuse triangle is. It's a triangle with an angle, at least one angle is 90 degrees. And inside a unit circle, remember we heard the term unit before in reference to a normal. That was a normal with a length of 1. So a unit circle is a circle with a radius of 1. So to calculate the value at different angles, essentially, of this triangle inside this unit circle, sine is essentially opposite divided by the hypotenuse. So remember, we had our three edges on our hypotenuse triangle. We had the opposite, the adjacent, and the hypotenuse. If we took the length of the hypotenuse and the opposite and divided those, we would have the sine. And there is a command in Maya that allows you to calculate the sine, called sine. And the cosine, which essentially be the adjacent length divided by the hypotenuse. And you can also find that by using the cosine command. So this is all very abstract, so let's go ahead and look at an example so it'll be a little bit clearer. Let's go ahead and open that here. So here we have our unit circle. Remember I talked about a unit circle. This is our unit circle here, radius of 1. Okay, so from here to here it's a length of 1. And here is our hypotenuse triangle. So this angle here, always 90 degrees, right here. So here's our hypotenuse and then our adjacent and opposite. Okay, so what happens is essentially, if I press play here, we have, remember I said, a hypotenuse triangle rotating around a unit circle. So this purple point here is essentially where these two angles connect to the edge of the circle, and it goes around like this, okay? So now if I back this up a little bit, you can see here that this length here is going to be 1 divided by the other, and that's going to be our cosine, and this is going to be, rather our sine, this is going to be, again, the hypotenuse divided by another one, and this is going to be our cosine in this case, okay? So the length of this edge here is 1, and the length of this edge here of the triangle is another, and that's what essentially sine and cosine are. So you see, as I rotate this triangle around, it's going to generate sine and cosine. And remember how I talked a lot about how a unit length of 1 and how triangles and how unitized things and are all really related to geometry and trigonometry, rather. This is a very good example of how they are related. So now if I move over a little bit here, you'll see something that looks very familiar. I'm sure you've seen this before, a waveform. Okay, so waves that go up and down. Now as I play, you'll see this yellow line here represents where this purple point is touching on the circle. So the yellow line intersects with either this red or green line is going to represent the point along this this curve that it's generating. So you can see on the left here we have -1, 0, as we have 1, 0, and -1. So the sine and cosine values that we have, for example, at this point here match up, and this is going to be about 0.7, okay? And here, let's say the cosine is at 0 and the sine is at 1. And anyway, as we move along here, you can see how the sine and the cosine move over time. And the input that these two commands take, the commands that you saw here before, the input that sine and cosine takes is this angle here, the angle of the triangle. You can see here this purple line here. What we feed sine and cosine is this angle. And what it's going to result is the lengths of these two lines, or, in other words, the point at which they intersect with this yellow line along here. Okay? So the way that sine and cosine work is you give it an angle, and it's going to give you, in this case, it might give you a number larger than this, but a number between 1 and -1 that represents the position of these curves along here. Okay? So the anatomy of a waveform. Essentially, a waveform has two elements: frequency, which is essentially the time it takes to complete one full cycle, and then the amplitude, which is the height of the wave. So, if you look at this example here, the frequency would be this. So, the tighter these are together, the more they're going to repeat. So you see, if this ends here, then it's going to repeat again and again and again. So it's going to go through a full cycle more if it's tighter together. And then again, the amplitude is the intensity, the height of the wave. So you see, if I bring this down, I have lower amplitude. If I bring this up, I have higher amplitude. So here, the amplitude is going to be between 1 and -1. If I do this, it might be between, for example, 2 and -2. If I bring it here, it might be between 0.5 and -0.5, etc. So now, to control the frequency and amplitude, we would use, for example, sine, and x would be the angle that we would put in this case. And if we wanted to have a faster wave, we'd multiply it by, say, for example, 0.5. Because if we had, let's say, for example, something that was going to only loop once, and we multiply by 0.5, we're going to cut it in half, and therefore we'll have it go twice. And therefore, in this case, the amplitude, the wave will be faster. It'll repeat twice. And if we want to have increase the amplitude, then we can multiply something on the outside. For example, we want to take the final result and double its intensity. So in this case, if we did sine and then put our angle, then multiply on the outside by 2, we would essentially be multiplying the result by 2. We would be increasing the intensity or the amplitude of the wave. So what would we use to model the movement of water? Well, here's a sample formula that I made up. Again, I'm sure there's a much better formula than this. So what I'm doing is taking the sine and then the frequency of the wave, and I'm using the frequency as the angle for the cosine, and then multiplying all that in the end by an amplitude multiplier. So I want to have more amplitude or less amplitude, I can multiply the result on the outside. So this will allow me, by using sine and cosine and having them interact with each other, to create a sort of false water effect. So here's how it would look in MelScript. I would use the sine command and the cosine inside, and then I had two variables, one for frequency and one for amplitude. So let's go ahead and open up that tool to see how this would work. So we have our water waves example here, and I'm just going to press play, and you'll see there's we got our water bouncing, okay? And this is essentially the wave that it's using right now. So if I go ahead and open the tool, it's going to allow us to control this stuff. You see, as I increase the frequency, this wave gets tighter and tighter because it's going to be repeating more and more, and you can see how the water is now moving much faster. If I bring the frequency down, you can see this wave is getting flatter and longer, so you can see the water is moving slower. Now let's up the amplitude. You'll see as I move this amplitude up, you can see our wave is getting taller and taller, and you can see as a result sort of a stormy seas effect we're getting where the water is moving up and down. And let's move up the frequency, and we get very, very intense sort of, it looks like bubble bath water. And let's move the amplitude down, and now we get sort of a babbling brook effect, where we have sort of a stream in a forest, where we have the water moving very, very fast but not very high. And this is the sort of wave that would represent that sort of thing. So that's a very, very short tutorial on everything you need to know about using sine and cosine and how it relates to trigonometry. So in conclusion, included in the eDVD support files, you have documentation that documents everything that you've just seen. You have all the scripts that you've just seen. You have all the scenes that you've just seen. So not only the scenes that describe all the mathematical concepts such as barycenter coordinates and Pythagoras, etc., but also all of the example scenes to try the tools out on, the mesh for the ambient occlusion and the water scene and the one that you just saw, etc. They're all there. And then finally, of course, the reference handout that I mentioned at the beginning that you can use that has all of the formulas and little bits of MelScript as well. I just want to thank Autodesk, of course, for allowing me to do this eDVD and for making all of their software, and of course the company that I work for, Artificial Mind and Movement. And thank you very much for watching. If you would like to contact me, if you have any questions or any comments, I would welcome you to go to my website, www.davidlightbound.com, or email me at info@davidlightbound.com. Thank you very much.